Hello, hello. My name is Robert Adut, and welcome to yaymath.org's presentation of YayMath in studio in beautiful Los Angeles, California at the YouTube headquarters called the YouTube Space LA. This is a beautiful facility that allows content creators like me and the people in other rooms to create videos and add to their libraries. And today we're adding to YayMath's library on videos certain things that I need to fill in our particular catalog with regards to Algebra 1. And this time we're talking about solving compound inequalities. And by compound, we mean more than one statement, separated by and or. So let's jump into this. YayMath! All right. So let's talk about this one first. This is compound because we see we have two inequality signs. And so we ask ourselves, with regards to the two statements here, as in -1 less than 2x minus 3, as well as 2x minus 3 less than or equal to 7, do one or both of those statements need to be true? Do that need to be true? Or and? This one needs to be true. So the answer is and, okay? So if you look at it closely, we could have said, we could break this into two, and a lot of people actually like to see it this way. My eraser, here we go. They like to see -1 less than 2x minus 3 and 2x minus 3 less than or equal to 7. And that's totally fine. You can solve both, okay? This word and, by the way, is code for intersection. Intersection. All right? And by intersection, it means both need to be true at the same time, okay? There's a fancy symbol for intersection. Basically looks like this. All right, that's the symbol for intersect. And the reason that I can remember this is that I just think of it like loop. It looks like an ant, you know? So, but you don't put that there. It's just for us to know. So this thing means intersect, which is code for and. Both need to be true. However, what's cool is that you can solve this little sandwich. I like to call it the sandwich. Get it? Get it? 2x minus 3 is sandwiched between the -1 and the 7. Okay, so this little sandwich can be solved algebraically. Let's put it down, it's fun. Sandwich. Meaning that if you see this sandwich thing, you know that it's an and. Okay? Teacher tricks. So, let's isolate x. All right, in order to do that, we need to get rid of the 2 and the -3. We've learned in previous videos, algebraically speaking, that we want to move this 3 over first by adding 3 here and here and here. You could add 3 to all 3 components and it'll level out. It'll be even. All right, I'm going to bring the work down here. -1 plus 3 is 2. Less than comes down. This is just like a little aside. So let me put that in like a pink box just so you see it's another way of looking at it. There you go. So that's equivalent to this. But now that we're coming back in, -2, we can switch to blue. Use go, is less than 2x, less than or equal to 10. And we are one step away. We're going to divide everything by 2. So this goes 2 and here and here. Divided, so 2 divided by 2 is 1 less than x less than or equal to 10 over 2, 5. So what this is basically saying is that x is sandwiched between 1 and 5, and your next goal will be to graph this on a number line. It's pretty cool. So if we have 0 here, we have like 5 here, we have 1 here. X is essentially between the two, not including 1. So when we want to not include a number, we do this open circle thing. So that's everything up to 1, but not including 1. And then we come over and la 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 la, and then close it on the 5 because it's or equal to 5. So in this case, x could be 1.000000001. You're like really, really close to 1, but not including 1. And over here, x can be 4.9, 4.99, 4.99999, 4.99999, and 5. That's why we include 5 that way, okay? So one compound inequality is this concept of and. The next one is the concept of or. Let's put this one down. You can't do an or statement as a singular statement. It won't work because sometimes both are true and sometimes only one is true. In fact, sometimes none are true. So in a sense, we have to be ready to like separate them. That's the idea. So let's go ahead and go minus 5, solving for x in the house of negative 2x less than or equal to negative 1 minus 5, negative 6. Divide both sides by negative 2. Whenever dividing both sides of an inequality by a negative, this sign flips. There's a video on solving inequalities. You could check that out, and you could see why. There's an intuitive proof as to why that happens. So negative 6 over negative 2 is 3. So we have x greater than 3. Or, let's go ahead and solve this. Subtract 4 on both sides. Subtract 4, 4. And we get x is less than 2 minus 4, negative 2. So you have to ask yourself, can both of these be true at the same time? Not really. Not really. Let's prove it on a number line. Okay? So here's 0, here's 3, here's negative 2. What we could do to really paint this picture nicely is that all this stuff will be the blue graph. X is 3 or more. X is greater than 3. So we go closed circle. To be greater than means bigger. Bigger means to the right. And then over here, say it's the pink stuff. X is less than negative 2, meaning not negative 2, but below it. Less than means small, open. And so, is it possible to be blue and pink at the same time? No, it's not, right? So any number that makes one of these happy will make this a true statement. You think of a number like 5. 5 is greater than or equal to 3? Good. So this is a true statement. X can be 5. X is allowed to be 5. Or negative 5. X is allowed to be negative 5. It doesn't make this happy because negative 5 is not blue. But it does make the pink happy because negative 5 is less than 2. All right? So think of it that way. One needs to be true. Both don't have to be. So the code word for or is called union. And union, the fancy symbol for union, is U. Okay? In which both don't need to be true, only one needs to be true for it to be an overall true statement. Okay? Now I'm going to do some sort of exceptions with the or and the and. Suppose I had x is less than 5, or, picking up on the or, x is greater than or equal to 3, let's say. All right? We have to think what numbers make this or both true, because that's what or basically means. Or means if one of them is happy, or the other is happy, or both is happy, both are happy, then you could say the overall statement is true, right? Kind of like a good example would be, suppose you went out Saturday night and you did not go out Sunday night, right? And I asked you on Monday, hey, did you go out on Saturday or Sunday? Your answer would be yes, because you went out on Saturday, but you didn't go out on Sunday. But because I asked you or, you said yes, since I went out on Saturday. The answer is yes, I did go out on Saturday or Sunday. okay? But if I had asked you, hey, did you go out on Saturday and Sunday? Your answer would be no, because both would need to be true. You didn't go out on Sunday, you did go out on Saturday. So since both weren't true, the answer for and is no. In other words, it's harder to do and, because both need to be true. Let's see about this or, Saturday or Sunday. What numbers are less than 5 or greater than or equal to 3? Let's check it out. Here's 0, here's 5, here's 3. I'll move 0 a little over, a little space. That's good. Okay. Less than 5, we'll make them blue. All numbers less than 5. Put that in a little box. 5, open circle. Less than means left. All right? And then 3, greater than or equal to 3 is in green. So we can go closed. Greater than means right. Cool. What numbers are less than 5 or greater than or equal to 3? In other words, asks what numbers are blue or green or both? Can you think of a number that's blue or green or both? I could think of a lot of numbers that are blue or green or both, Like 0. 0 is blue. 0 is covered by the blue line, so 0 is blue. That means 0 makes blue happy. Is 0 less than 5? Yes. So it doesn't matter that 0 doesn't make this happy. 0 is not green. 0 is not greater than or equal to 3. But 0 works. 0 is a solution to this compound inequality. What about 4? 4 makes this happy. 4 is blue. 4 makes this happy. 4 is greater than or equal to 3. So since it makes both happy, 4 is a solution. What about 10? 10 is green. 10 doesn't make this happy, but 10 makes this happy. So I tried every single number I can think of is blue or green or both. Every single number is actually covered. So the answer to this compound inequality is all real numbers. Here's the fancy symbol for all real numbers, a capital R with 2 lines. You could try drawing it. It's fun. All real numbers. Meaning any number will make one or the other or both happy. Okay? Let's try a different one though. What if I said x is, let's go with less than 4 and x is greater than 6. All right. So here's 0, here's 4, here's 6. Let's go with the blue again. This is blue. Open circle on 4, less than means small. All right, and then this one was green. Open circle on 6 to the right. There it is. So and asks both need to be true, all right? So what numbers are blue and green? What numbers are both less than 4 and simultaneously greater than 6? Can you see numbers here that are blue and green at the same time? I saw them here, but I'm not seeing them here. It turns out there are no numbers that are blue and green at the same time. There are no numbers that make this happy here and this happy simultaneously. And since and needs both to be true, there is no number that makes both true. Try as we may. We could say 3, but 3 doesn't make this happy. We could say 10. 10 makes this happy. 10's greater than 6. 10's not greater than 4. So on this is like the opposite side. So, no solution. No solution. All right. So now I'm going to ask you to get your bodies involved in this learning. All right. So let's give it a whirl. If or goes like this, that's cool. Okay. If or goes like this, that's cool. Because numbers are either here, smaller than something, or greater than something, and not both. If and goes like this, that's cool. If and goes like this, we're thinking what the overlap is. All right, so let's actually get those. So here's when or going like this. Let's do it, that's fine. Or, that's fine. This is a fine answer for or. So we go here. And then we go here. And if this was an and problem, that's cool. Because and asks about overlap. And so the overlapping section would be this. So that would be the final answer. You could shade that part. Some people erase. So that's cool. But this one here, what happens if you have and like that? Try that. And. Is it possible to have overlap here with this and? So if this isn't ever an and problem, when they diverge like this is no solution. And then if you have an or that's converging, you have or going like this, as well as this. What numbers are covered by, let's go pick a different color here. What numbers are covered by black or green? This can be, now let's say blue or green. What numbers are blue or green or both? All numbers are blue or green or both. So in this case, when you have or going like this, that would be all reals. That's essentially all the major ones, you know. And you could think of other ones that sometimes they go in the same direction. You can handle those right now. Give them all to you. So you have them all good to go. Give them all to you. So we have like here and here. So if this was basically or, we could just kind of leave it, you know. If that's or, that's fine. Technically, it's, you could start from here. Because right, only one needs to be true, or both. So or, it's fine to just leave that. You know, there's no harm in that. But with and, right, we have here, boom, and requires overlap. So if this was an and problem, we would have to explicitly shade. Let's do something like, I'll pick the pink again. I'm having a lot of fun with these caps. Mix and match, and pink and green here. So we have to explicitly shade the overlap for and. So that's really every scenario, okay? Or going like that, cool. And going like that, cool. Overlap, shade them or erase the sides. And going like that, basically not cool, impossible for both to be covered like this. So no solution. Or going like that, kind of weird because all numbers are covered here. All numbers are covered by this, or by both. So in that case, or converging is all reals. And then when they go in the same direction, or is fine, you know, overlap or one, and though requires a bit of shading, okay? The last thing we'll do with regards to this is if I gave you the graph, you come up with the compound statement, right? All right, or and. Or and. Traditionally, this looks like an and because it's like and overlap. It's not looking like this where one or the other can be true. So I'm feeling like this is an or and this is an and. Since it's an and, we can do the sandwich. Boom. This is pretty much the format for the sandwich in which we're or equal to the bottom one and not or equal to 5. Go small to big in this case, small to big. So we put -1 here, we put 5. And it's true, x is now greater than or equal to 1, meaning -1, excuse me. X is greater than or equal to -1 here to the right. And x is less than 5, right? So both of these are true. Whereas over here, x is what 0? Smaller or bigger? Well, looks like we're going to the left, so that's small. X is what here? Smaller or bigger than 4? Looks like we're going to the right, so bigger. Can both of these be true at the same time? Or. There you go. This is an and statement. All right, cool. That's all it is. Thanks for being with us. Cool. Yay, Math.